In this lecture, we'll discuss several examples of linear systems, and for quite a few of these, we'll show the properties of homogeneity and additivity. Our first example is the bucket system, and I like this system because it's one of the easiest for the student to understand. All you need to do is to understand basic volumetric relationship. So let's suppose that we have a bucket and then we have water flowing into the bucket. And the water flow rate is given by signal x of t. And this is the volumetric flow rate, so it's measured in something like centimeters cubed per second. Our output in this case is going to be y of t, which is the water height measured in centimeters. These two variables are related by the equation shown at the bottom of the page. Here the coefficient a is the area of the tank, and that's in centimeters squared. So you see on the left the total response y of t, that's the height of water in the bucket. Y at time 0 is the zero input response. That's what would happen if we put no input in, that is, if the flow rate was 0. And then the last term consists of 1 over a times the integral from 0 to t, x of tau d tau. Now that integral is the volume of water that's been put in since time 0. When we take that volume and divide by a, we get the increase in height due to the added water. So you can see the total response, which is the height at the current time, is equal to the initial height of the water in the bucket plus the increase in height caused by adding the water. The term 1 over a times the integral is the zero state response. This is the response due to the input alone. So you can see we have the total response is the zero input response plus the zero state response. Let's now show that the water bucket system obeys superposition. So the equation you remember for this system was y of t is equal to y at time 0 plus 1 over a times the integral. If we look at the response due to just the input alone, this would be y of t equals 1 over a times the integral. Since y at time 0 is the response to the initial condition. If the input was x1 of t, the output would be y1 of t equal to 1 over a times the integral of x1. If the input was x2, the output would be y2 equal 1 over a times the integral of x2. This is the basic setup to check superposition. So now we'll look at the case where the input was x3 equal to k1 times x1 plus k2 times x2. The output in response to this input will be y3 equal to 1 over a times the integral of x3. So we'll substitute in for x3 k1 times x1 plus k2 times x2. Then we'll divide that integral up into two parts and pull the k1 out of the first term and the k2 out of the second term. And that will give us k1 times 1 over a integral of x1 plus k2 times 1 over a integral of x2. Now the integral of x1 divided by a is y1, and the integral of x2 divided by a is y2. So we find that y3 is equal to k1 times y1 plus k2 times y2. We've just proved superposition for this system. There's one more thing that I'd like to point out before we move on to other examples, and that is here we're working with the linear bucket system. There is such a thing as a nonlinear bucket system. We'll study that in another lecture, but for right now let's discuss the difference between the linear and nonlinear bucket systems. The key aspect to this problem, the linear system, is that the shape of the bucket is cylindrical. And what that means is that there's the same surface area no matter what height the water is. If we look at a nonlinear bucket system, for example the conical shape shown at the bottom of the page, the surface area changes as a function of the height of the water in the bucket. This will make the differential equations between the input x and the height of the water in the bucket y nonlinear. Here are some other examples of linear systems. The first one is a very common form, which we'll study in detail later. It is a linear differential equation. The second one is our moving average system. In the third, the output is proportional to the input, with the constant of proportionality varying with time. In the fourth system, the output is a delayed version of the input. And in the fifth system is a time-scaled version of the input. For all these systems, you can prove superposition in a very similar fashion to what we did for the water bucket system. Here is a very common form of linear system, which we'll see again and again in this class. In fact, it's the primary form which we'll study. Any system described by this ordinary differential equation form is a linear system. The only thing that's required is that the coefficients a0 through an and b0 through bm are not functions of the signals x or y. You see on the left-hand side of the equation that we have derivatives of the output up to the nth derivative. Each of these derivatives is multiplied by one of the coefficients, a0 through an, and they're summed together. On the right-hand side, we have very similar terms, except for these are derivatives of the input signal x. Like on the left-hand side, these are summed together, and that's important. If the terms are not summed together, then the equation is not a linear system. Now it's important to point out that while the coefficients cannot be functions of the signals x or y, they may be functions of time. While the differential equation form is very important, it should be pointed out that not all linear systems have the differential equation form. Of the 5 systems that we introduced before, systems 1 and 3 have the differential equation form, but systems 2, 4, and 5 do not. I had mentioned previously that the second system was the moving average system, and had stated that it was linear. Let's now use the superposition property to verify this. We'll proceed in exactly the same fashion as we did for the water bucket system. So we'll look at two different inputs, x1 and x2, and find the response of the moving average system to these inputs. We'll label these y1 and y2. And then we'll come up with a new input, x3, which is k1 times x1 plus k2 times x2. Then the response to this will be the moving average of x3. We'll then substitute in for x3 k1 times x1 plus k2 times x2. After substitution, we'll break up the integral into two terms, and we'll pull k1 out of the first term and k2 out of the second. So y3 is equal to k1 times the integral from t minus cap t to t of 1 over t x1 of tau d tau plus k2 times the integral from t minus cap t to t 1 over cap t x2 of tau d tau. Those two integrals are y1 and y2, and so we find y3 is equal to k1 times y1 plus k2 times y2, and this again is the property of superposition. So why are these systems called linear? Let's forget about the systems at all and just look at a line, which consists of all the points which are related by y equals mx, where m is the slope of the line. So let's suppose we have 2 points that are on the line. One is x1, y1, and the other one is x2, y2. Since these points are on the line, they obey the equation of the line. So y1 is equal to m times x1, and y2 is equal to m times x2. Now if we pick a new x value, call it x3, which is equal to k1 times x1 plus k2 times x2, the corresponding y value will be y equals m times k1 x1 plus k2 x2. We can then distribute the m over these two terms, and then commute the k1 with m and the k2 with m. And we'll find y3 is equal to k1 times y1 plus k2 times y2. So we have superposition. So why are these systems called linear? It's because they obey superposition. And points on a line also obey this principle. This principle of superposition is the key difference between our two worlds, our world of order and our world of chaos. In the next lecture, we'll discuss the world of nonlinear systems.